Uh, Hello everyone. Let's start. In this lecture, we will continue the study of the Fourier transformation. In particular, we are going to prove the Paley Wiener theorem from two techniques. One is shifting line of integration, which we used in last lecture, and the other technique is new, which we are going to prove. It's called Fragment-Lindelof theorem, which is a generalization of the maximum modulus principle to unbounded domains. So actually, the idea hidden in their proof, it is used a lot widely in PDE and all kinds of analysis technique to derive the Liouville type theorem. When we prove it, I will give some more information on the background. So first, let's start with the following function, f, which is in L2 space in the region -m to m. So in other words, we can say fx is 0 for all x whose norm is greater than m, and f norm square is integrable from on the interval -m to m. Okay, then define the Fourier transformation. Last time I mispronounced the variable. Here the variable is called theta. -infinity to positive infinity, fx exponential -2 pi I x theta dx. Since f is 0 outside the interval, so the interval can be simplified to a well-defined Riemann integral. Okay, so proposition 1, f theta is well-defined for all complex number theta. So proof, we write theta as Xi plus I eta. Xi eta are real numbers. Then from the definition, we know f hat Xi, norm of f hat Xi, less than norm of f times -2 pi I x times Xi plus I eta dx. Okay, and you simplify, you find this is fx norm times exponential 2 pi x eta dx. And then we use the Cauchy-Schwarz inequality. So this is f norm square integration, take square roots, times integration of exponential 2 pi x eta norm square, take roots. So here we use Cauchy-Schwarz. If you forget, please read Rudin's book. I think it's in the second half, within the material 522. So which says integration fg. So absolute value less than or equal to integral f square, take square root, integral g square, take square root. Okay, now for the first part, by assumption this is bounded, and the second part is integration of smooth function. It's also bounded. So finally, this is bounded. Therefore, f hat c is well defined, but I would like to see f hat c is defined as a Lebesgue integral, not a Riemann integral. So if you haven't learned real analysis, then probably that's a little bit tricky part. So Lebesgue integral, I'm not going to explain what is Lebesgue integral, but basically this means f is not necessary to be continuous nor bounded. The only assumption we use here is norm square the integral is less than infinity. Okay, so if I want to explain Lebesgue integral, probably I need to spend another course to tell you what is a measurable set, what is Fourier measurable, what is Lebesgue integrable. Okay. I highly suggest you to read Rudin's another book, Complex Analysis and Real Analysis. And secondly, we are going to prove that although f is not necessary to be continuous, but after the integral, the property is much better. The Fourier transformation f hat theta is continuous. So the proof goes as follows. To prove the continuity, we just check the definition. So we compare the difference. So this will be less than or equal to norm f times exponential negative 2 pi I x theta plus h minus 2 pi I x times theta norm dx. So this will be from negative m to m fx exponential negative 2 pi I x times x times theta n times exponential negative 2 pi I x times h minus 1 dx. Then by Cauchy-Schwarz, this is less than norm f squared dx 1/2 times square root of integration of exponential negative 2 pi I x theta squared times exponential negative 2 pi I x times h minus 1 norm square dx. And this you take a square root. And it's clear this integral is independent. So the first term is bounded, and second term is integration of some smooth function. And you see when h goes to 0, this is O size OH, or you just expand this as negative 2 pi I xh plus high order terms and then do integration. So it will be OH when h goes to 0. Therefore, we prove that by definition, f hat is continuous. And thirdly, we are going to show that f hat c is differentiable. And the derivative partial eta f theta is negative m fx exponential negative 2 pi I x theta times 2 pi x dx, and the partial cos f hat theta is integration negative m to m fx exponential negative 2 pi I x times theta negative 2 pi I x dx. So the proof, here we will prove this just from the definition. Suppose, so we consider the following quantity: f theta plus IH minus f theta minus IH times integration negative m to m fx exponential negative 2 pi I x theta times 2 pi I x dx. Yeah, actually I can use some fancy theorem to conclude you can interchange the order of derivative and the integral, but sometimes it's hard for me to remember the theorem, and it's easier to give the proof directly. It's not that hard. Actually, this is also the way we prove the uniformity guarantee the change of orders of certain operators. Okay, then if you plug in the Fourier transformation for f hat, and by a similar way we can conclude that the quantity is less than or equal to integration norm f times exponential negative 2 pi I x theta plus IH minus exponential negative 2 pi I x times theta minus IH exponential negative 2 pi I x theta times 2 pi x dx. Okay, then this is less than by Cauchy-Schwarz norm f squared dx 1/2, and then integration negative m to m integration negative 2 pi I x cos plus IH minus exponential negative 2 pi I x times cos minus IH exponential negative 2 pi I x times cos times 2 pi x square dx, and the square root. Okay, so first is bounded, and second one is a smooth function, and then you can expand, you will find it's O large OH squared as h goes to 0. Therefore, by definition, derivative cos of f hat theta is given by derivative partial eta negative m to m fx exponential negative 2 pi I x times theta 2 pi x dx. And similarly, we can take the other derivative and prove this is differentiable. Exponential negative 2 pi I x times theta negative 2 pi I x dx. Okay, next, proposition 4. Thus we can show that f hat cos is holomorphic proof is from the here partial 可see f hat equals. So from the derivative formula, you see the right hand side is also integral. Therefore, you can do the similar estimate and show that the derivative are continuous. Then apply Cauchy-Riemann operator. It's easy to check that Cauchy-Riemann operator hits on f hat is 0. Therefore, f hat is holomorphic. Okay, now before we state the theorem of Paley Wiener, we would like to make a remark. So here, the most important assumption on f is supported on the interval -m to m. Without this assumption, your the analysis will be much harder, because if you double check all the details, you will find if the integral is from -infinity to positive infinity, then all the estimate you are doing fails, because the good part we are talking about it's divergent if m is positive infinity. Okay, that tells you if you know some information or f like vanishes outside or decay very fast, you expect the smoothness or its Fourier transformation or the holomorphicity. So if you are brave enough, then like Paley and Wiener, then we can guess the following theorem. So let f be a complex valued continuous function of quadratic decay on R, then f is the restriction of R of the entire function on C with growth condition, growth controlled by fz norm less than or equal to a exponential 2 pi m times z for some positive a if and only if the Fourier transformation f hat of f is supported on -m to m. So let's do a remark. So before we discuss the problem, suppose you have function f on R, how to extend f to C as a holomorphic function. Usually it's very hard, but this theorem tells you if you know this is a Fourier transformation, and if you know the Fourier transformation is good, then we can do this. Okay. Now, before we proceed to prove this theorem, let's state and prove a generalization of maximal modulus principle. It's called unbounded domain. It's called Fragment-Lindelof theorem. So for 0 less than beta minus alpha less than 1, let omega be the open sector bounded by argument z equals pi alpha and argument z equals pi beta. So let f be a continuous function on omega head such that f is holomorphic on omega and fz norm less than or equal to m on boundary and fz is norm is less than a exponential norm z gamma on omega for some a greater than 0 and the angle gamma is the power gamma is less than or equal to 1 over beta minus alpha, then fz less than m on omega bar. So if you draw a picture, it says, suppose you have sector, okay, and where the function f is defined, and suppose on the visible boundary of omega, so the function is bounded by m, and on the invisible boundary, that is infinite place, you put on some gross condition, that is f norm less than or equal to a exponential z to gamma's power, then your conclusion is f is bounded by m on the whole domain. So you cannot have any growth. The growth condition forces the function to be constant. This is called the Liouville type theorem. So actually, this is called the Liouville type theorem. There are a lot of study of this in differential geometry, geometric analysis, and PDE. So a typical type is, suppose you have function f satisfy certain conditions or solve some equation, and plus you have some growth condition. For example, it's at most quadratic growth or whatever, then we are going to derive something like f must be constant or must be linear function or whatever. So this kind of growth condition for some rigidity. Okay, and the remark 2 is, whenever you see some estimate, you should be very careful about the critical case. So when gamma is 0, then what do you have? Then this is just the so-called the original, similar to the original Liouville theorem. And when gamma is when gamma is 1 over beta minus alpha, the theorem fails. Why? Because now you look at the function fz equals exponential negative I beta plus alpha divided by 2 times pi times z, and take beta minus alpha's root. Okay, then you can check this satisfies that. Of course, if you take the norm of this one, so recall the real part of the exponential is less than or equal to the norm of the number. So so f norm will be less than exponential z norm gamma, where gamma is 1 over beta minus alpha. And if you check the boundary, so look at, let z be exponential I beta pi times some t is a real number. Then you plug in, you find the f, this kind of f gives you exponential I beta minus alpha divided by 2 pi, and take 1 over beta minus alpha's root, and times t. Okay, then this whole thing, the index will be imaginary, will be some imaginary number, so it will be exponential I pi t, so it's exponential it, so it's an imaginary number. Not imaginary, it's cosine pi over 2t plus sine pi over 2t. So if you take the norm, it's less than or equal to e. And similarly, if you take z to be exponential I alpha pi times t, you get the same thing. Therefore, f is bounded on boundary by a constant. But of course, this function is not bounded on the whole sector, so it contradicts with the theorem if you relax the condition to allow gamma to be 1 over beta minus alpha. Okay, from this, actually, we already have some idea. So next, we use a auxiliary function to help us. This is also the common technique used in PDE. That is, if your function, you don't know, so the main idea is improve your function epsilon beta, and then show that the epsilon beta satisfies the conclusion. So first step, you do a weak version, prove something for a better function, and then let epsilon goes to 0 and show that the epsilon beta converges to the original function, which satisfies the conclusion as well. So how to get the epsilon better, usually you need to have some auxiliary function. Sometimes we use plus g epsilon, so this will be auxiliary function. And in this case, in our case, we try to times auxiliary function a. Here we times some auxiliary function such that it's better. So proof. So without the loss of generality, we can assume that beta is positive and alpha is negative beta, so it's symmetric around the axes. And let g epsilon z be a function exponential negative epsilon z to eta's power fz, where epsilon is positive and eta greater than gamma but still less than 1 over beta minus alpha equals 1 to beta in our setting. Then it's clear g epsilon z less than or equal to exponential negative epsilon norm z eta cosine eta pi beta times a times exponential z to gamma's power on the whole domain omega. And in particular, if we choose norm of z larger enough, so we can show that g epsilon z norm less than or equal to m for all norm z greater than r z in omega. So the idea is like, suppose you have, so here you have sector okay, then if so your auxiliary function g epsilon, it still might be very bad in the interior. It will be very large, g epsilon interior, but on some far away boundary outside this region, g epsilon will be small. Okay, this is because this angle is less than pi over 2. So cosine this angle has a lower bound. So norm of this has a lower bound. So for example, it's greater than delta, and therefore the whole factor is less than or equal to negative minus epsilon delta norm z to gamma to gamma's power, and now to eta's power, now plus z to norm z to gamma's power times a. If you choose z bigger enough, since eta is greater than gamma, so this index finally will become very small if norm z larger enough. Therefore, it finally can cancel out a and give you the bound g epsilon less than m. Then you consider the following boundary. Consider a region, or let's denote this radius as g epsilon because it depends on epsilon. Let's assume when it's greater than or equal to g epsilon. Okay, so consider the bounded region. So omega bar intersect the ball z less than r epsilon, less than or equal to r epsilon. Then it is clear we can apply maximal modulus principle to this region. Hence, g epsilon z less than m on omega hat z less than r epsilon. Okay, and here since noted that for the region outside the ball with radius epsilon r epsilon, we already know g epsilon z is bounded by m, then g epsilon z is bounded by m on whole omega hat. Therefore, fz is exponential epsilon z to eta's power times g epsilon z is bounded by m times exponential epsilon zeta eta's power absolute value on omega hat for any epsilon greater than 0. And in particular, let epsilon goes to 0, we conclude for any z in omega bar, fz is bounded by m. Then we are done. So all the condition is applied here. So this is the crucial part. To make sure you do have a correct auxiliary function. Okay, then next we are going to apply this corollary. So if fz is holomorphic on C and fx is bounded by A on the real number line and it's bounded on the whole domain by A exponential 2 pi m norm z for all z in C, where A, M are positive numbers. Then the conclusion is you can have a better estimate. You can bound the norm of f just by its imaginary part. So you see here the improvement. Originally, you assume it's bounded by exponential 2 pi mz, but now it's bounded by 2 pi m absolute value imaginary part. So the proof, so let gz equals fz times exponential 2 pi I mz, then of course gz norm less than equal to A on the real number line and on the positive imaginary axis. Okay, this is because if you take z equals to to positive iy, so fz is less than equal to a exponential 2 pi m y, and then this factor is bounded equals exponential negative 2 pi my. Therefore, fz less than or equal to normal fz less than or equal to a normal g less than or equal to a on the imaginary axis. So now you have control of these two lines. We consider the function g on this region, R1 we call. So by applying Fragment Lindelof theorem to G on the first quadrant with angle alpha is 0, beta is 1/2, and gamma is 1, so of course it's less than 2, equals 1 over beta minus alpha. Then we can conclude that we have G is bounded by A on the first quadrant R1, and in particular A, so Fz equals Gz times exponential negative 2 pi I mz. So the norm of this is bounded by A times exponential 2 pi m norm of y. Y is the imaginary part on R1. So similarly, we can bound F on the quadrant R2, R3, R4 separately, all by the growth condition. This one. R3, R4 by this condition. So we are done. Okay, now we state another lemma. If fx on R is continuous with quadratic decay such that f hat theta is also a quadratic decay, then we have fx is the integral of f hat theta times exponential 2 pi I theta x d theta. So we will prove this later. This is another version of Fourier inversion theorem. Recall that previous we proved the same type of statement for f defined in a small stripe along the axes. So here our assumption is that f probably don't have any extension as a holomorphic function. You only have growth condition, decay condition. So how do you prove this? Then this will be a little bit harder. We will leave it to the end. Next, we first prove the Paley Wiener theorem. So we first prove the condition this direction, that is, if f theta is supported on negative m to m, then f has a the theorem claims that then f has a holomorphic extension as an entire function. Okay, so let me repeat this. So we are going to show that if this is true, then f is the restriction of an entire function. Entire function means holomorphic on C. Is entire function on C and with a growth condition less than exponential 2 pi m z hat a m greater than z bar. Okay, this direction is easy because since you have compact support, then of course f hat has quadratic decay, exponential negative 2 pi I cos x dx. Okay, this will be just integration from negative m to m, the same integrand, and then define. This is by the previous lemma. Actually, you can show f has a by showing f has quadratic decay. Okay, next, so how to show this actually? Yeah, you can do integral by parts to show this. I will not repeat it. Just leave to you. Okay, next let's define fz. So whenever you have integral representation, you can easily extend it to all the complex numbers. You just change it to cos z dz, and notice that this is just negative m to m f cos c exponential 2 pi I cos z d cos c. Sorry. And notice that fz. So let's call it f. Okay, I still use the notation f. Okay, then f coincides with fx on the real number line because they have the same integral representation. Okay, so it's an extension of f, and f is holomorphic. This is what we proved before at the very beginning. And thirdly, let's look at the growth condition. So y, so since this is less than or equal to f hat zeta norm times inside you will have exponential 2 pi I m z norm. So we are done. So next, let's prove the other direction. So if fz is holomorphic on C and fz norm is bounded by a times exponential 2 pi m norm z, then we are going to show that f hat C is 0 for all C norm greater than capital M. So an idea is we shift the line, so f zeta equals integration x on real number line fx exponential negative 2 pi I zeta x dx equals x in real number line fx minus iy exponential negative 2 pi I zeta x minus iy dx y greater than 0. And we want to use this type of formula to do the estimate. But then the problem is, if you look at the line, so actually what you are doing is shifting the integration line. But then if you construct a contour to derive this, you need to estimate the vertical sides, the integral on vertical sides, such that when n goes to infinity, the vertical side goes to 0. But then the problem is, if you look at the vertical side, the exponential part, exponential negative 2 pi I C x here. It's underneath the row axis. Okay, so when this is negative pi theta times y. But then the problem is, if theta is, for example, is negative, then this arrow turn blows up instead of going to 0. So this estimate kind of not enough. You cannot shift the line directly. Okay, so you need to improve your estimate a little bit. So by this part, we need to use the Bregman Lindelof. So suppose f norm is less than exponential 2 pi mz norm on C, and fx is bounded by constant a. then by the Lindelof fragment Lindelof, we know that fz is bounded by a times exponential 2 pi m, the real part, the imaginary part. Okay, now you define a better function, f epsilon z, fz equals fz divided by 1 plus I epsilon z square, where epsilon is greater than 0. Then let's do the pointwise estimate of f epsilon zeta minus f hat zeta. So by definition, this is given by f epsilon x minus fx exponential negative 2 pi I zeta x dx. And this is integration fx times 1 over 1 plus I epsilon x square minus 1 exponential negative 2 pi I zeta x dx. Okay, then by dominated convergence theorem, so in real analysis, that means if, so the exact statement like the following. If g epsilon is bounded by function g for all x on R, and limit g epsilon equals f, then pointwisely for all x in R, then we have limit integration g epsilon x. Also we need to assume, and integration g is less than infinity. Then we have the integral converges to the integral of fx. So any domain omega, omega, omega. So this is called dominant convergence. If you have some function dominate each of the function in the sequence, and the dominant function is integrable, then the sequence of functions, then the pointwise convergence gives you the norm convergence. Okay, then here look at this function. So notice that this is bounded by 2 norm fx, and f is integrable because okay, so you need to because we know f has quadratic decay. Okay, at the very beginning, so and f less than infinity, since f has quadratic decay. By assumption. Therefore, you can use, and also this goes to 1 as epsilon goes to 0, and for all x in R. Then we can conclude that as epsilon goes to 0, f hat epsilon theta equals f hat theta for all theta real number. Okay, then to prove the Paley Wiener theorem, then it suffices to prove that f epsilon hat theta equals 0 for theta for norm of theta greater than m. So for this part, just look at recall that f epsilon x minus I y. So by the Fragment-Lindelof theorem, this is less than a epsilon exponential 2 pi m absolute value of y 1 plus x squared. So 1 plus x squared comes from the quadratic decay of the denominator. So y. Okay, then the Fourier transformation f epsilon hat c, the norm is we can integrate in this way is x in r f epsilon x minus I y exponential minus 2 pi I c x minus I y dx. So less than or equal to a epsilon integration exponential 2 pi m minus zeta absolute value of eta 1 plus x squared x in r dx. So less than or equal to b epsilon exponential 2 pi m minus c times eta norm eta. Sorry, here is y, here is y. Okay, let y goes to infinity, then f hat epsilon theta equals 0 for all theta greater than m. So similarly, we shift the line integral to f epsilon hat theta equals fx plus I y exponential negative 2 pi I theta x plus I y dx, and do the estimate for all theta less than negative m. You can apply the same technique. So the reason why we can shift the line is because, just like here, it's because now you can control the boundary. Because here you have negative. So this is dominated by this quantity, and this quantity vanishes on the vertical side. So just look at here. The vertical side is here. So you can estimate this vanishes on vertical sides as n goes to infinity, or as blue line, so green lines. becoming infinity. Okay, then you are done. And then you can shift the integral, and after shifting the integral, then you take y goes to positive infinity. Then you can conclude the Fourier transformation of f epsilon is 0 outside when zeta bigger than m. Similarly, you can do the shifting. Okay, so the key idea is you need to have some decay so that you make your function f a little bit better so that you can control the vertical size. And to make your function a little bit better, you need to times in the horizontal direction this factor and control this in the y direction. That means the norm of f should be controlled in terms of the imaginary part, which is independent of the horizontal part. Okay, so please digest this proof. It's very delicate. I will stop here. Next time we will talk about the Fourier inversion theorem in a weaker condition. Just the lemma we haven't proved but used here.